Welcome everyone to this session of the AI Net Zero webinar series. My name is Sarah Perez. I'm a postdoctoral research associate at Heriot University, and it's my pleasure to chair today this first session dedicated to early career researchers from a research group funded by the UKRI Core on artificial intelligence to enable UK net zero targets. So today we are delighted to host two speakers, namely Dr. Hibist Kassa from the University of Leicester and Dr. Benaissa Dekhici from the University of Surrey. So please join me in welcoming them and feel free to engage anytime in the discussion by writing your questions or comments in the YouTube chat. And before we start, I just want to remind everyone that you may need to log in with a Google account to leave any comment on YouTube. So please check already if you can have questions, because we will have a Q&A session at the end of each talk. So without further delay, let me introduce our first speaker of the day, Dr. Benaissa Dekhici, who is a postdoctoral researcher in Bioenergy Process Optimization and Control at the University of Surrey. He holds a PhD in mathematics from the University of Leiden in Algeria, with a focus on the optimization of anaerobic digestion processes. Dr. Dekhici current research conducted in collaboration with the Supergen Bioenergy Impact Hub integrates advanced data-driven techniques and digitalization strategies to enhance the efficiency and sustainability of bioenergy production. His work bridges the gap between theoretical research and practical applications, aiming to drive innovations in the field of bioenergy. And today he will give a presentation titled Integrating Advanced Data-Driven Techniques in Bioenergy, Insight from Anaerobic Digestion Process Optimization. So Dr. Benaissa Dekhici, thanks for being here first, and then the floor is yours.
Well, thank you so much, Sarah. Thank you for having me. I'm pleased to be here in the AI for Net Zero webinar. As you have already mentioned, I will be presenting integrating advanced data-driven techniques in bioenergy insights from anaerobic digestion process optimization. Well, first, I will give you a brief introduction of myself and already my experience. I hold a PhD, as you have already said, in automatics from the University of Tlemcen in Algeria. This is the map of Algeria, and this is like my hometown here. I work mainly on data-driven modeling or the reduction and control of anaerobic digestion processes. I also been an Erasmus exchange student and bilateral student for 2 years from the University of Trento in Italy, in the north of Italy. And also now I am a postdoctoral research in bioenergy process optimization and control at the University of Surrey. As you can see here, I'm working with the Supergen Bioenergy Hub, which is a hub that works in digitalization of bioenergy in general. So I will give you a brief introduction about what is anaerobic digestion and why we are working on this kind of technology. So anaerobic digestion, basically it's a natural process where microorganisms are trying to break down materials without the presence of oxygen and produce some really valuable materials like biogas, which is considered as renewable energy, and also some kind of digestate that can be used as fertilizer. So in the industry, people try to understand this dynamical behavior, and they try to put these polyethylene materials in some bioreactors in order to understand the underlying dynamics of the anaerobic digestion process. And there are so many configurations how to study this or how to work with this. The most famous bioreactor in the industry is the continuously stirred tank reactor, where we maintain a constant volume and we have an inflow rate, outflow rate. So as you know, in order to understand this, we use some mathematical tools and create some equations in order to understand, predict, and control this kind of phenomena. So in the literature, we use the mass balance law in order to extract mathematical models. These models, they have been here for decades, and these models are based on the ordinarily differential equations. Even though that these models have done a really good thing in order to try to understand the dynamic behavior, but they lack a lot of predictability because, here we are working with living kind of microorganisms, which is difficult to write down. We cannot even agree on a mathematical equations of the dynamical behavior of these creatures. So there still be a huge gap in order to understand what is going on under the hood of AD. Before going into some technical work here, I will just want to give you an idea why AD, why actually I'm working on this bioenergy, why this is really interesting. So this is the map of the UK, and here you can see like different sites or AD sites or plants that are working on AD already. So the UK has invested a lot in this technology in order to reach the net zero strategy or to be carbon free, of course. And there are a huge amount of energy or renewable energy has been produced from this kind of technology. And also by using AD technology, the UK can actually reduce its reliance on fossil fuels and decrease the overall greenhouse gas emission, which is really bad for the climate change, of course. There are so many challenges on this technology, mainly the complexity of the AD. And also there are different feedstocks and different materials that can be used. For here in the map, you can see that for the square, this is farm fed. It means that it's used agricultural feedstock, and the circle is for waste fed. So it's used wastewater or even food waste, and so on. So in our work, what we are trying to do mainly is trying to take advantage of existing mechanistic models. By mechanistic models, so first principle models, they have already been working with some mathematical models, and then we take them, we work with them as virtual bioreactors in order to generate some data, and we take advantage of the explosion of AI and machine learning nowadays, and try to find some substitute of this mechanistic models. We will substitute them with the data-driven model. So the idea is really basic. We start from data. This is what we have, and then we try to construct dynamical models. So this is what we need, dynamical models. What it means dynamical models? It means that we really need to understand the underlying dynamics. We need to know what is going on with this kind of technology. So with these models, of course, have to be interpretable and generalizable. Machine learning models. There are so many techniques in the literature. You can see that AD has been already interacted with some machine learning methods, but even you can use neural nets here or neural networks, but these models are not interpretable. You cannot understand what is going on. So we were been focusing on this method, which is really famous back then. This is the Koopman operator theory. It's a very detailed method or theory where we can actually take advantage of this technique in order to generate or reproduce models. So the idea is really basic. I'm not going to give you a lot of details that to bother you with some mathematical equations and so on, but the idea is pretty simple. Let's say that we have nonlinear object, and this object is difficult to handle. We lift it to infinite dimensional linear object, so we still are working with a linear object, but it's difficult. If we can try to use this kind of approximation or try to truncate or try to take what we really need, we can end up with a finite dimensional linear object, which is going to be easy to work with or to handle. So some mathematical formulation on this method. Let's say that we have a dynamical system, x dot equals f of x. We lift it to a higher space where the behavior of this nonlinear dynamics will sound linear, but still infinite dimension. We use some data-driven method in order to approximate a matrix from this infinite dimensional linear operator. So this is a matrix. By matrix, I mean a constant coefficient matrix that tells us how the nonlinear dynamics is moving. We try to understand very easily by looking at the eigenvalues and eigenvectors of this matrix. So before going through to the application of this method to this kind of technology, which is AD, we have to understand, we can use this mechanistic models. We need to understand what people were doing before. And the most basic model of AD is the chemostate model, or the model consisting of two equations. The first equation of substrate, the second equation of is the biomass. And even though this model is pretty simple, as we can see, but it is strongly nonlinear. We have two equations, but you can see that mu s, this kind of function, is the specific growth rate. This is how the biomass is actually acting or growing with respect to the substrate concentration. In AD, you can see that there are two famous ones. There is the first one, which is monotype given by this function. It's like we have rational nonlinearities, which is even really complicated and difficult. And also we have Haldane type. We have like rational nonlinearities and also quadratic nonlinearities, which is making this simple model is very, very nonlinear. And there are other models. The other one, which is a little bit complicated, is like this two-step model, or the two-step acidogenesis methanogenesis model. So the model is considering the AD in just two steps: acidogenesis step, where we have a specific group of bacteria that is degrading the substrate, of course, and another group of bacteria called the methanogenesis bacteria that is transforming this another substrate to the biogas. Well, the model is consisting of 4 equations and is taking advantage of both mono and Haldane type, which makes this model descriptive compared to the smaller or the simplest model of the chemostate. And this model has been introduced in for 2 decades now, and it was mainly taken, we're working with wastewater treatment, wastewater feedstock, which is a specific feedstock, which is another challenge in our case. And for those who are a little bit familiar with anaerobic digestion or modeling, they might have heard of the International Water Association Anaerobic Digestion Model number 1, or ADM1 for short. This is the most detailed, complicated, and phenomenological model. It describes the ID on mainly five steps. 4 are biological steps. And imagine that in this model, we have 35 state variables or 35 equations like the previous one. So this model is very high dimensional. We cannot use this model for control. It's so difficult and complicated. And in order to calibrate this model for our devices or our reactors, we have to calibrate more than 100 parameters. This model also was introduced 2 decades, and it's mainly working with wastewater treatment. Can be adapted. People they are doing so many hard work in order to adapt this model for their type of feedstock. So this is just the first building block of our work, is to understand this mechanistic model and try to enhance this kind of AD modeling thing. In terms of the application of the equipment operator theory in order to model that purely using data, this is really important. We do not have any idea about the mass balance and such kind of things. So first we need some inputs and state measurements, either from experimental or from simulation. We embed with some kind of functions. You can use they call it nonlinear observer functions. This function will lift our nonlinear dynamics into higher space, and we use some kind of methods in order to approximate the Koopman operator K, this one that advances this kind of function or measurement forward in time linearly. And of course, we will have a linear model. We can use this linear model for things like state estimation, future state prediction, and control. And also, we can restrict our modeling scheme by saying that we do not have a full state measurement. So let's say that we are not measuring the bacteria or the microorganisms. This is so difficult. We do not have a tools or sensors that can give us a continuous way to monitor these concentrations. So we can just use data and use the Koopman operator theory in order to predict the output of our device. And then we use some very famous linear control design scheme. So in our case, we use model predictive control. And I will give you just a quick overview of MPC. The idea of MPC is pretty simple. We have a plant, we have an input, and we have an output. We want to change or to control our plant by measuring our output and controlling the plant by some generated input, of course. So the idea of MPC, we need to have a model. This is really interesting. So if your model is linear like this is linear MPC. If your model is nonlinear, it means that you have nonlinear MPC. So the idea is we need to use some state estimators. We used our model, we construct some future output, and we have an optimizer that is like minimizing or maximizing a objective function, and we have some constraints. And we will generate a set of control input. We will be using just the first input to the plant and also to the model, and at each time we try to generate this kind of input in order to update the control input. This is so powerful nowadays. MPC, it's going really well with Koopman, of course. So those are some results here. We have here tried to control, to model and forecast the chemostat dynamics as the two states model. It's a really basic model, as you saw, but it's strongly nonlinear. And you can see that the Koopman model is trying to follow any sudden changes in the real system. And we have compared here the results with some famous local predictors, as you can see. The Koopman model was capable of capturing purely from data, of course, the main dynamics of the real nonlinear system of the chemostat, which is really interesting. And also we have used a restricted measurement scheme. We have measured just the substrate in order to control the output. Of course, in our case, this is the substrate. And also we have compared Koopman MPC to the linear MPC, where linear MPC is taking the advantage of using a local linearization of the dynamics or the chemostat model. You can see that the Koopman MPC is like following this time value reference tracking here and without evaluating any constraints. And the linear MPC was not even capable to work really well with even there is infeasibility. And with regards to the ADMR model, we tried to reduce the model from 35 states to the states that are more important and dominant. And what we have done exactly here, we have taken the measurements, all the states. So we have just measured the states of the ADMR model. We have stacked them into a vector, as you can see. So we have x1, x2, until x35, and we have made a snapshot in time. So x1 is your concentration and time 1, x2 is your concentration and time 2, and so on and so forth. And we have reshaped these data matrices. Here we have x is all your measurements of your model, of course, of your system in time 1, time 2, until your time period. And we have used this kind of x prime, which is the same as x but shifted one data t in the future, as you can see. So we can say that this is xk plus 1 and this is xk. And we used this dynamic mode decomposition, which is a data-driven technique in order to obtain linear reduced order models for high-dimensional complex system like the ADMR model. The MD is so basic, it's just 4 or 5 lines in Python MATLAB. So just apply the SVD for this big data matrix X, and we can just take the first dominant PUD modes for people who are familiar with statistical analysis like PCA, or this is just your PUD modes, and we can project your data matrix A. This is the operator A that tells us how our states are evolving in time. And then we can take a look at the dynamic modes, the amplitude, and also we can have like a reduced model. This is our reduced ADMR model, linear reduced ADMR model, which is really powerful. And also we can reconstruct our original data or our original states by just projecting the reduced model to the PUD, the U matrix from the SVD. As for the results, the ADMR model has 35 states. Here I have tried just to put 9, but the other ones are pretty similar, because what we have used here, we have used a reduced order model for just 7 states. So we have reduced the ADMR model from 35 states to 7 states and reconstruct the data and compare it with the original ADMR model. This is so powerful. It was just a naive application of the MD without having any idea about the ADMR model and the equations, just the data coming from it, of course. Also, instead of having just a matrix, just the dynamic, we need also to control sometimes. So what we have applied DMD with control, which is similarly as DMD, but this time we will incorporate control in our linear model. So we will have two data matrices as x and x prime, and also epsilon, where epsilon has our control input at each time step. Here in this study, we have used AM2 model, the model with just 4 states, and we use this data as an input for the DMD algorithm, and we reconstructed a input-output state space model. And of course, we need to do some validation here. We have applied a different validation control for a longer period for both the original AM2 model and also from the DMDC model, and compare the measured with the simulated, of course. Here we have like the results. You can see that the training data was for 100 days, and you can see all the concentration are following the original system, which is really important sometimes when you want to do control in this kind of models or technologies. You have to rely on some really simple models in order to take the process further. Here we have like this is the work with my collaborators at the University of Trento in Italy. They've been working on the coupling between anaerobic digestion and hydrothermal carbonization. And just to give you a quick overview of HTC, or hydrothermal carbonization, there are other technologies in bioenergy, not just anaerobic digestion. There are pyrolysis, gasification, and HTC. HTC is pretty simple. We use some biomass feedstock in HTC reactor, where we put high pressure and high temperature in a specific timing, and we can get some really good output like hydrochar and so on. So they have been using some kind of HTC or digested-based HTC products in a continuous digester, and they were monitoring pH and some other parameters, and they want to say that this is going to enhance biogas production, like remove the concentration of the pollution and so on. Here we have done a really classical way of mechanistic modeling. What we have done, we take advantage of the AM2 model. We have modeled it, we have modified the specific growth rates and some equations in order to add the pH dependency and so on and so forth. And this is the output of the model, where you can see, even though that the biogas measurement was extremely noisy, the AM2 model was capable of at least following the trend of the biogas production. At the end, I will just give you an overview about what I am doing actually here at the University of Surrey. I am working on rapid digitalization of bioenergy for high efficiency and profit. And I am working under the umbrella of the Supergen Bioenergy Hub, which is a hub that collaborates with academia, industry, government, and social stakeholders to advance sustainable bioenergy system, aiding the UK shift to low carbon energy future, and of course, achieving the net zero targets. The UK has invested a lot, as I already said, in the AD. So our goals will be mainly pretty simple. We need to integrate a whole site model or digital twin. So this is like the idea of digital twinning in this case. Imagine that we have a process. The process has some sensors taking some recordings, and the output of the sensor is going to digital twin. Digital twin try to apply different control schemes or control techniques or decision-making techniques or outputs, and choose the best one to take it to control the actual process. So the idea in our case, we try to find optimal real-time decision-making tools, and also in order to enhance process flexibility and control, we want also to integrate uncertainty-aware predictive modeling in the mechanistic models. And of course, we aim to deliver a roadmap and open source toolkit at the end of the project. We are working with our industrial collaborators in order to ask them to understand more about digitalization of this under digitalized, if we can say, bioenergy technology. And also we aim to use rapid digital twinning for site-wide optimization and control. At the end, I would like to thank you for your attention, and if you have any question, you are welcome.
Thank you, Benaissa, for this very engaging, insightful presentation.
Thank you.
highly encourage the audience to post a question in the chat. I don't see any for the moment, so I will start with some of mine. So you mentioned that some of the more realistic models, like the ADM1 model for anaerobic digestion, involve like 100 of parameters.
Yep.
So I'm wondering, in your approach, how do you like calibrate these parameters? Is it like included in the Koopman reduction model, or do you need to deal with this in another way?
Well, what we have done here, we have taken the benchmark model of the ADMO model. So the model, we took the model as a virtual bioreactor. So the model was already calibrated and published in so many works. So we take just the already the original model with the calibration from the wastewater treatment or from the original article. And what we have done, we have generated data from this model. So we said that this is a virtual bioreactor, and let's see what we can measure. In the case of the ADMO model, we can measure 35 states. This is not doable in real time. There is no bioreactor that can tell you what is the concentration, or we cannot measure the concentration of different species or microorganisms. And we have used DMD, where DMD is a data-driven approximation of the Koopman operator, where in DMD we use just the states instead of any object or any embedding function that can alleviate or lift the states, the space. So in this case, we have just given a data to the method, and the method that has nothing to do with what is going on in the ADMO model. And we have reduced the model and got a reduced version. So the method was capable of telling us more about ADMO model.
All right. And then what's the sensitivity to these like parameters? Because if I understand correctly, your data are somehow sampled from like a stochastic distribution of these parameters, right? Coming from either lab measurements or...
Sorry?
So how is your response depending on the variability of these parameters and so on in your data?
Yeah, so we actually we haven't done any sensitivity analysis in this case, but it sounds that the MD has been improved a lot in the last years, and they have shown that the MD is a little bit robust compared to other methods that are based on this data-driven technique in terms of noise, not in terms of the sensitivity of the parameters. So if you have noisy data, you can get really good approximations and reduced patterns from your system, of course.
Okay, thank you. So in the meantime, we got a question for Muhammad Malrutu Hassan. What have you done for information loss due to dimension reductions?
What have you done for information loss?
Do you want me to repeat the question?
So, yeah, you can just reformulate it again.
So he's wondering if there is any loss of information coming from the dimension reduction in your linear order reduced model.
Okay, so when the ADMO model first has launched, it was in 2002, and since then people were trying to, specifically in control, we are control theorists. We work with control a lot, so we do not like to have like really complicated 35 state ODEs to work with. It's not convenient. So people were trying to reduce the ADMO model. There have been used so many techniques. There is variable association. There is PCA. People have been using to reduce the parameters based on PCA or perceptual component analysis. So in our case, we have taken an idea from these papers or these works that the ADMO model can be actually reduced to 7 states, because those are, from most of the works, the ADMO model has been reduced to 7 states, and those states are usually the most important states in AD. In our case, we take a look to this DMD or singular value matrix here, and we were like trying to truncate, as you can see here, the important singular values. We left just 7, and these 7 states were really, really capable of reproducing the original data, which means that there are some hidden states, or there are
Yeah.
some states in the ADMA model in order to reproduce the original data, which is so powerful. So we were like taking just 7, which is enough in our case.
All right. Thank you. Really interesting.
Yeah.
And I will continue with like a more general question for putting your work in perspective, I would say. So how does anaerobic digestion processes contribute to broader sustainability goals? Because I'm not familiar with the process. And yeah, so how do this help like promoting sustainability?
Well, the anaerobic digestion is, as I said at the beginning, it's a really promising technology. It's not really new. Actually, anaerobic digestion was here for more than 50 years, and even the models have been like have been people have been working a lot on modeling this kind of technology, and you can see that the UK has invested a lot in this technology, and there are so many challenges that will hinder, of course, sustainability, or hinder like feedstock variability, or there are so many people are working toward this, and we are actually engaged in a project called AI for AD. So we try to make AD a data-driven technology. And also you can see that AD can solve many problems in terms of the greenhouse gas emissions, or also producing electricity, and make the UK targets for net zero much easier compared to other technologies.
All right. Awesome.
Yeah, thank you.
So if we don't have any more questions from the audience, we think we can thank again Dr. Benaissa for his presentation,
Well,
and
thank
we
you.
can move to our second speaker of the day. So
Well, thank you.
our second speaker is Dr. Hibist Kassa. She is a policy interface fellow at the Institute for Environmental Futures in the University of Leicester. She is an associate editor with the Agrarian South Network Research Bulletin, which is a tricontinental network of researchers in Africa, Latin America, and the Caribbean. Hibist was awarded a doctoral in sociology from the University of Johannesburg on petty commodity production in artisanal and small-scale mining in Ghana and South Africa, which was funded by the National Research Foundation of South Africa. She has worked in feminist organizations and policy research institute in Africa over a decade, and is a former Development Alternatives with Women in a New Era executive committee member. She is currently working on a forthcoming book on petty commodity production and artisanal and small-scale mining, which is part of Breer's new political economy series. She has published on academic and popular platform on artisanal mining policy, land, social reproduction, conflict in Africa, and political economy of natural resources. And today she will give us an introduction to the challenges of translating policy goals, priorities, and approaches into a digital twin. So Dr. Hibist Kassa, thanks for joining us today, and the floor is yours.
Thank you very much for inviting me into this space. And just to start off, this presentation is going to focus on the policy dimensions, as you said, of developing a digital twin. I don't have a computer science background, neither am I an environmental scientist, as you highlighted earlier, but applying from policymaking processes, experience in that both globally and regionally. The project in itself is seeking to develop policy with impact to create to use the digital twin as an instrument for policymakers to then simulate real-world conditions and test scenarios. To begin to outline what the challenges are, I'd like to start off by looking at the global policy challenges and then going through the UK policy context and highlighting the elements that are framing the narratives emerging and how that then is being input into the digital twin in terms of the framing of the questions. You'd see that the questions are more focused, particular, they need to be more precise, as opposed to the more broader framing and questions and queries and challenges that revolve around unintended consequences of policy decisions and in terms of outcomes and competing interests. So in terms of the global policy challenge, of course, the IPCC synthesis report speaks to a range of things from unequal historical and ongoing contributions arising from not only unsustainable energy use, but also land use and land use change in terms of patterns of consumption and production that have been unsustainable, that have been destructive across regions between and within countries. And then in terms of ecosystem-based adaptation as approaches that can actually be effective in reducing the extreme weather events, particularly flood risks, urban heat. Questions also about how the global greenhouse gas emissions in 2030 are likely to exceed 1.5 degrees during the 21st century. And we already saw that in February this year. The first indication of that. And in relation to this, as the crisis continues to mount, so is the gap between the projected emissions and from between projected emissions and the kind of policies that are to be implemented in relation to the nationally determined contributions that countries have signed up to, that have volunteered, and the gap between that in relation to the finance flows, shortfalls that exist. So there's a great deal of policy, if you will, a leadership crisis at the global level, across all sectors and across all regions. But then in the UK, so do similar patterns emerge. And in fact, the loss of global leadership has been something that has been highlighted. The Climate Change Committee, however, in making recommendations, and just to highlight, the digital twin is, it's not just scenarios in all conditions and circumstances, it's focused on lowland, peatland, and in ruminant production. So in relation to this, the Climate Change Committee's recommendations that I highlight here have to do with then the challenges or the framing of what farm changes are needed to be able to improve emissions intensity, they say. So in terms of thinking about the carbon intensity of agriculture and how it can be reduced. And the question of not just looking at technical measures and productivity improvements, but also behavioral change that's required to reduce emissions from soil and livestock, which is what the digital twin is focused in relation to lowland, peatland, and ruminant production. So the reduced demand of carbon-intensive products is something that is recommended in terms of having a shift away from livestock production towards crops. And in terms of sustainable farming, innovation and technical measures alone are not enough. You need to have a strong policy framework to integrate the innovation and technology alongside shifts in the public diet. The absence of strong measures in relation to this has been something that has been highlighted by the Climate Change Committee, and this puts emissions reductions at risk. So the policy recommendations also relate to productivity and low carbon farming systems for arable and livestock production. So the use of peat and agriculture management needs to change in terms of how it's been set up. Of course, there's creation of new woodland and sustainable management of woodlands, but alongside that, with peatland restoration that has been highlighted. In the post-Brexit context also, there's been a challenge with not having clearer policy coherence across the nations. And that continues to be a pressing problem that has been highlighted by also not just the climate change community, but also emerging from, say, for example, the National Union of Farmers. So the UK policy challenges also emerge in relation to other questions and queries about the approaches being adopted, concerns around carbon offsetting and how this may permit fossil fuel industry, weapons manufacturers and airlines to continue to pollute, and therefore not taking any measures to reduce emissions. So these tensions kind of play out subtly in terms of the Scottish woodlands that has a restricted approach to carbon trading in woodland management, and that has experienced some pushback with a desire for more if you will, a more liberalized approach to it, to speak loosely about that. In terms of greenwashing techniques, there have been superficial changes to product packaging, minor increases in plant-based products, while not addressing the emissions across the supply chain. And this been critique in relation to the supermarkets that 95% of emissions actually comes from sales, and the drive to encourage the overconsumption. So the continued overconsumption of meat and dairy, which has an effect on production, also relies on feedstock imports that puts pressure on agriculture and ecosystems elsewhere. So the globalized nature of livestock production emphasizes the large carbon footprint that's been highlighted by UK soy consumption impacts on the Amazon, for instance. But there have also been concerns around low carbon requirements added to trade agreements and how this may impact on less competitive farmers, such as family farms, and also importers to the UK, and the NUF has been making demands around this. Climate change also impacts on farm practices. So farm practices that previously thought to be sustainable practices may, due to the dynamic conditions created by the climate crisis, extreme weather events, may have consequences. There could be more damage, and the same applies to tree planting. So in terms of the UK policy framing, in England in particular, the Agricultural Transition Plan has sought to at least achieve 40% of to turn 40% of agricultural soil to sustainable management by 2028 and 60% by 2030. Protect 30% of the land and of the sea in the UK for nature's recovery. That's the 30 by 30 strategy. And around this, it's framed around three policy goals. And what is particularly of interest in relation to thinking through different scales is thinking about how ambition and scale in relation to the kind of farm practices, the relation to the kind of targets that you're setting up, in terms of the kind of innovation that you're introducing at scale, at different levels of scale, and how that plays out. How do you be able to do it in the right places and joined up ways to deliver the target outcomes that are required? And so this emphasizes the idea that this ought to be place-based, but also be able to move through different scales simultaneously. So the UK and England, the transition plan is framed. The schemes are oriented to work at scale, but at the same time have some degree of flexibility within the scheme, encouraging and enabling effective action. Farmers undertaking ambitious actions are provided premium payments to cover high risks, but there are also limits in terms of parts that deal with the historic environment. And so the flexibility limit then is set up there. But there's interest in trying to understand, or this is learnings from feedback from farmers in terms of what has worked and what hasn't worked, the evolution of the policy landscape in the UK, and as it has played out in England. So the land use change continues to be like a real conundrum or a challenge in terms of thinking through how to approach a decision between preserving biodiversity on agricultural land and whether to concentrate it in certain areas while managing biodiversity elsewhere. Is that the approach? So this is a question that Green, Balfond, and Palan pose, and is highlighted as a guide in terms of the methodology they developed for policymakers. And in their conclusion, they would say that their findings largely draw on emphasis on restoring or creating non-farm land, so land sparing, as opposed to land sharing. So to be able to pursue policies that would enable land to be dedicated for to preserve biodiversity or for restoration, as opposed to having it occurring alongside each other on the same field or farmland. So the Green Alliance also speak in a 2003 report highlights how a small number of farms on lowland peat which produce cereals have a carbon footprint higher than that of what's of soya grown on deforested land in the Brazilian Amazon. And this, given that greenhouse gas emissions are so high, reducing them by rewetting land would be highly lucrative, and they make a case based on economic modeling. So the narrative emerging is around this, the value that could be attached to restoration of nature, and in particular to the differential impacts and the way in which the economy in the UK is linked to the global, has a global footprint in itself, and how to respond to that. So the England Peatland Action Plan then sets out the government's long-term vision for maintaining and protecting and restoring peatlands. And what would be of interest in relation to this, the crafting of this digital twin, is that there are, of course, competing land demands in terms of food security, nature conservation, as well as others, housing. And all of this has social implications. And to be able to, for policymakers, it's a challenge of being able to weigh the co-benefits or the risks posed by decisions that are made on how to, in terms of land use and land use change. So in relation to this, the Institute for Environmental Futures had a long-running project, and that developed a report making landscape decisions to meet net zero carbon emissions. And in this report, it emphasizes that they must be place specific across all scales, and from the scale of a designated landscape down to the field corner. So it requires thinking around this, and this is what the digital twin is set up to be able, or is being designed to respond to, in terms of the need to be able to think through multiple scales, but also at the micro level, and to enable thinking about the targets and emissions, but also other impacts that are likely, the unintended consequences, the trade-offs that may be necessary. So in relation to this, and in terms of thinking about peatland management, one of the things that are of core concern has to do with the water table depth. And so the decision between a balance between CO2 emissions from drained peatlands, or to be able to result in methane emissions from rewetted peatland, like to find a balance between these two forces that or emissions that emerge out of the management of the water table depth. Now, existing policy emerging as of May this year has been seeking to prescribe what that can look like. But as I said earlier, there are a whole range of things that can impact on the water table, in terms of the different dynamic elements at play. So for instance, depending on the kind of fertilizer that you're using, in relation to the target outcomes, depending on the kind of conditions created by the climate crisis. So all these elements may have an impact to undermine or improve or worsen the conditions within which particular prescriptions are offered, and to enable achieve the targeted outcomes. So this creates questions around what the room of compromise is going to be, and it is for this end that the digital twin, as a representation of the physical environment, has been set up to respond to. Now, the use case that is being drawn upon for the peatland restoration is in East Anglia. The East Anglia Fens is worth about, in terms of what it's generating as a commercial farming area, intensive farming area, it's £3 billion per year. It's healthy, and normally healthy peatlands would capture CO2 through photosynthesis, but for agricultural purposes they have to be drained, and then that results in them becoming a net source of greenhouse gas emissions due to how they are managed. As I said earlier, this is an ongoing concern from the climate change committee right down to the reports that I've highlighted, that managing the peatlands is of a key concern to reduce emissions and find a balance. And this largely has to do with the water table depth, but not only. So 1 meter of peat takes like 1,000 years to be created, but 1 to 2 centimeters is lost due to oxidation every year. So that shows you that there's also a gradual degradation that's taking place of the peatland as a result of intensive agriculture activities, the drainage that has been happening, as well as other elements and practices that may be harmful to the environment. Now, it's not to say that farmers don't have a concern or prioritization in relation to environmentally sustainable practices. In fact, a colleague on the project, John Maltby, has done research with about 400 farmers, drawn a survey with 400 farmers, and one of the insights is that it's a priority for farmers, but at the same time, to be able to understand what the actual impacts are going to be, you'd need an instrument to test in a very dynamic and complex context, because it's also changing. It may cost up to 8 to 22 billion pounds per year to restore peatlands in the next 100 years, but it may cost actually 109 billion pounds. It would save 109 billion pounds of reduced carbon emissions. So the challenge is finding a coherent land use policy that will integrate the questions about how you're able to deliver your objectives in terms of responding to climate change and reducing greenhouse gas emissions, but also achieving your agricultural objectives. And what are the trade-offs? What is the likely, if you will, impact of decisions that are made? What are the unknowns? So in relation to this, with the ruminant production, what has been emerging as, if you will, a progressive model, or what has been put forward as one that has within the nations of the UK as having a decarbonized beef production, has been in Northern Ireland. Now, it's interesting to highlight that the meat industry has in itself articulated and conceptualized and adopted an approach and a strategy that they had to be able to attain this outcome as stakeholders engaging with the Department for Agriculture, Environmental, Rural Affairs in Northern Ireland, has been oriented to this, to be able to encourage producers to finish prime cattle at younger ages. So if they don't live as long, then the emissions are per cow or is reduced, for instance. So in terms of this has also created room for questions around investment in genetics to deliver good carcass quality, according to the meat industry, genotyping program, strong knowledge transfer programs. So this raises some questions in terms of or understanding about the policy coherence between the meat industry and the Department for Agriculture, Environmental, Rural Affairs in Northern Ireland, and it's reflected in the policy shifts that have taken place in Northern Ireland. But there's always the unintended consequence. So I'd like to just highlight this one study in 2022 that talks about how inorganic feed additives have remarkably reduced methane emissions from ruminants, but their usage as feed additives remain unappealing because of health and safety concerns. So that then becomes a policy concern in terms of the long-term impacts that this is going to have, and therefore recommendation that they offer is feed additives sourced from biological materials, such as direct fed microbials, and that being a promising technique in mitigating enteric methane emissions. So it becomes a preferable approach in spite of the remarkably reduced methane emissions from ruminants, because in an attempt to resolve one problem, you might be creating another, as they highlight in terms of health and safety. So this is the kind of thing that is of concern, and the project in terms of its analyzing around an analysis or simulations that will be generated could provide evidence that then will highlight or what is a preferable kind of option in terms of reducing emissions without causing harm or unintended consequences in the real world, and to be able to anticipate that. In relation to the peatland side of things, the way we framed the questions that are emerging, it's been drawn upon policy. It's also been reflected in policy questions that have emerged. So these questions have been, for instance, what is best grown, when, what quantity, for what purpose? So those are very precise questions. But also emerging is questions around what is the best practice for greenhouse gas reductions in a productive and biodiverse landscape? What levers may be required to establish such measures where you have land that's largely privately owned? So that's a policy concern, but in relation to this project, what would be relevant also has to do with how does climate change impact on high-grade farmland. So with East Anglia's would then be relevant. What are the spatial and temporal scales that play out in terms of short rotation forestry? This doesn't have direct bearing on the project, and the other has to do with energy crops that also doesn't have direct bearing on the project, because in the fens it's largely vegetable crops that they're producing. So what questions have been input into the digital twin? The variables have been the crop type, temperature, water table depth, yield, harvest, climate scenarios, and in relation or temperature, or the in terms of the scenario projections using the IPCC recommended, the IPCC developed scenarios. So the questions would be what to plant, how much to grow, water table depth, where does that lie, where should that be, when to harvest, what type of fertilizer reduces emissions, and this then further is developed in terms of in the process of refining what we have. So right now we're in the first section under questions, but we intend to develop it further with broadening and it all depends on the kind of quality of the data that it's available, the time period. So for instance, the temporal element is something that we're very much aiming to achieve. So instead of being restricted to present conditions and what the outcomes would be in terms of CO2 emissions, for instance, which is what we have for now in terms of the digital twin, but thinking about what the projections would be up to 2080. So that capability exists, and to be able to set up systems that enable the scenarios to then be displayed with an interactive software program. So that has been
Hibist,
yeah.
sorry, I will have to ask you to wrap up, please.
Sure. This is literally the last slide. So I just wanted to say that we already have that, and then the earlier last week's presentation, Professor Heiko Balzer did present and show a demonstration of the digital twin that you can look at on this channel. Thank you.
Yeah, thank you, and sorry for showing up, but we are running out of time.
That's fine.
So, yeah. So this is a really interesting topic, to be honest, and like a side topic of what we usually heard on this kind of thing. So yeah, thank you for the great talk. It's really interesting. So please, for people still in the audience, feel free to ask your question in the YouTube comment section. So I will start with some of mine. What do you think would be the ethical concern of using digital twins, highlighting like the trade-off you mentioned between economic constraint and policy calls for net zero, for instance? So how do you see like the ethical use of this kind of approaches and technology?
The ethics of it, that raises a key. It's something we've been in conversation about in terms of as we're setting up the digital twin, thinking about what our biases may be in terms of what we may be inputting into the digital twin, and how that then may have some consequences that we're unaware of or not been reflective about. There's also questions about how the digital twin could potentially be used. It's the technology in terms of its setup is largely set up in a way that the stakeholders are the ones who then make decisions. So it doesn't actually tell them what to do. So what it does is just illustrates and shows what the likely emissions are going to be. Now, depending on what the setup is and what it includes and what it excludes, it needs to be more explicit so that it doesn't provide, if you will, an unrealistic illustration of the real world conditions, even though it claims to show the real world conditions. So at the moment, it's at the earliest stage of if its development. But the hope is to be able to continue to build on what we have and to be able to show that capability and to be able to test scenarios in a way that it can be realistic, and to be able to be very transparent about in terms of its accuracy. So the good thing is that we have a number of data sources. So it's not just in terms of a simulation, but it also includes Earth observation. So there is like very, if you will, ground reality that's being input into it for us to then measure to show the extent to which it diverges from the real world conditions, and that then informs the whoever the user is in terms of its level of accuracy. And so that degree of internal reflection and conversation is ongoing, so in terms of the ethics, that's one concern, but also in terms of just the use of AI and in terms of its consumption of energy and so on. So it's still at the earliest stage of development, but we're reflecting as part of our commitments in terms of its impact. So in terms of the way the AI is set up, the digital twin is assumed to be using less power than a simulator that's already established, that is Joule's simulator. So we're working alongside both kind of simulations and to create a surrogate Joule's and the digital as a digital twin, and to be able to test the accuracy in relation to that. So the assumption is that the Joule simulator consumes a lot more energy and requires a lot more skills and capability to be able to manage and run it, while the digital twin is more accessible. But we know that AI's consumption of energy is much higher in real terms. So we are weighing this and reflecting that and thinking through how to make it more efficient so that its its carbon footprint is also reduced. So that's part of our internal reflections on that. So that's as much as I can say in relation to ethics.
All right, great. That's awesome. And so I think we can make the input variation of the digital twin based on the physical, like landscape or field. How do you incorporate like policy variability in terms of location? I mean, by that, you will not implement it the same digital twin, I guess, for UK policies and for like African or Latin American policies, right?
Yeah. Okay, so that's important. So the policy context does inform in terms of the requirements, needs, the design, the setup. So, for instance, when we have a conversation around scale and the way we think about scale, I think that to be able to understand that the different impacts it's required in terms of the UK, there is a commonality of desire to understand scale in relation to the ways in which the policy measures may impact, whether it's a large scale, macro scale, or a micro scale. But there are other questions. So that is the relational element. So for instance, the idea that if our advice is basically to say that you must restore certain areas because to be able to implement this policy, you'd be able to now restore peatland, you're storing carbon, but your footprint expands in terms of the Amazon, in terms of the destruction of the Amazon. Is that really an option? Is that really a policy option? If that is the orientation and approach, that then it has a relational impact elsewhere. But if we were to take this digital twin and apply it in another context, the impacts and decisions that we made about restoration also has a different relational impact in terms of livelihoods. So it's not just even just between countries. If you take the digital twin and try and apply it, let's say in the uplands, there are new questions that emerge in relation to the lowland peatland. There are new questions that emerge as a result of just the context and the questions about land tenure. So similarly, so it can be said in other regions of the world, like where you have different land tenure systems at play. There are different political questions, problems, social and economic problems that arise, livelihood questions that arise, and the question of also biodiversity. And of course, the question of who is managing those resources and who actually gets to control it. So those are political questions. And the digital twin doesn't necessarily reflect all those elements in it. All it can tell you as it's currently set up is looking at just looking at the kind of crop that you're able to grow and the kind of emissions impact that it may have in relation to fertilizer. But if you think about fertilizer and synthetic fertilizer in relation to organic fertilizer and the need to transition from it, the policy context in other countries may be hostile to that because of different pressures that exist. What is the likelihood of a transition from synthetic fertilizer and organic fertilizer taking place in the UK but not happening elsewhere? So that could be a concern emerging from that. But also, as I said earlier, there's also a trade implications about trade in terms of low carbon products being exchanged in the global economy. And so the assumption that countries that may not be able to meet those requirements then getting excluded. And that then becomes a barrier to trade, which has been an ongoing battle since the liberalization of and the emergence of the WTO and the kind of like negotiations that have been ongoing. That then adds a new element or a new area that requires further like reflection and engagement. So there are policy issues around the digital twin, but in terms of its design and its setup, doesn't necessarily reflect that. So the technology in itself can be applied in a different context. So hypothetically, if a different government were to emerge today in the UK, it could, with a different policy framework and approach altogether, so not in consensus with the range of assumptions that I had outlined earlier, it can still use the digital twin to test, but it will make certain decisions that maybe have different outcomes for good or worse, for better or for worse.
That makes completely sense. And to conclude, I would say like we need more interdisciplinary collaboration on this topic to make like the digital twin more ethical and sustainable for like everyone. So yeah, thank you very much, Sibi. It was a really interesting conversation. I could spend an hour talking about this, but we need to close the session right now.
Sure.
So let's thanks again to both our speakers for sharing their insights with us today. So I will really see today's session covered a diverse range of topics, showcasing the various applications of AI to achieve net zero objectives. So with that, I will conclude by thanking everyone in the audience. And please don't forget to subscribe to our YouTube channel, to ensure that you will never miss our future engaging webinars. So with that, thank you, everyone. Bye.